All right. Okay. Hi, everyone. So, two things about the midterm. So one is, well, the grades are out. If you haven't seen the announcement, it is here. I'm trying kind of in general to give people as good a sense as possible to the extent that it is possible in terms of how they're doing in the class. And my judgment was that the best way to do it was to say that I'm going to be adding 8 points to the raw average on the midterm, which would make the median, I guess, would be 70 in that case, because it started out as 62. Of course, kind of people's performance at the end of the day is going to depend on how people do on the exam. That is not information that I have. That is possibly not information that you have. I will say that the information that I do have is that some people really need to practice more. In particular, so I'm doing this reweighting scheme. So basically, the midterm was worth 30%. And it can still be worth 30% for you if that is to the individual student's advantage, but we'll take the maximum between the midterm being worth 20% and 30% rather, and 10% of the midterm being moved over to the exam, again, kind of if it's to the individual student's advantage. So I want to strike a balance here between giving people hope and giving people something to work for, versus kind of giving people hope where it might be unwarranted. I got to say, yes, it's completely possible to improve on the exam. Every year, many people do. At the same time, many people do not. Like I said in the posts, for many people, the time to start practicing for the exam was this morning, so that's already gone. But after the lab this afternoon is fine as well. And you got to. So if you cannot write code that's kind of especially for the first several questions for the midterm, if you cannot write code that basically compiles, there's no expectation that you write something on paper and it compiles exactly. That's unrealistic. But it should be that it basically compiles. And I think for some of the midterms, what I saw is that that was not the case for some people. So it's easy, I think, to kind of fool yourself into thinking, if you're interacting with ChatGPT or if you bought Claude 3 or something and it helps you out, it's easy to say, well, I almost got it and Claude or ChatGPT got me there. Well, you got to actually check. So what you really got to do is sit by yourself at a computer, solve the basic problems. You compile it the first time. Probably there's going to be errors. Figure out where to fix them. Figure out how to make it so that the code actually works. I think if you do that with Q1, Q2 on the midterm, and you get to the point where you actually can do that, and the changes that you need to make are pretty minimal in terms of getting the thing to work. I think, well, at the very least, you should be able to do the first couple of questions on the exam as well. They're pretty similar. Please do that if you haven't done it. I know that in the lab, so we try to enforce it with the online exercises a little bit, but well, they're online exercises. In the lab, you work with a partner. I think maybe not for everyone, but I think for some people, that means that maybe you are not exactly estimating where you are correctly in the course. So make sure that you sit by yourself, if need be, come to office hours and figure out where you are and where you need to be. So the regrade requests are, I'll just emphasize this because there's a bunch of people already who are not following the policy, and it's okay. If I told you on Gradescope this morning you're not actually following the policy, you can resubmit the request. It's fine, but please do follow the policy. So the policy is there's three kinds of situations. So one situation is your code is perfect, but we stole marks from you for no reason. That sometimes happens, and if that's the claim, you can say it. Of course, if you're wrong about that, we'll be annoyed. So what you should do is you should actually type up your code, try to run it, make sure that you're right and we're wrong. And if we're wrong, we're happy to give you the marks back, of course. Most of these cases are not like that. Most of the cases are you think that you deserve that, you made some small mistakes, but not commensurate rather with what we have deducted. So you basically got some partial credit, but you think you deserve more. And that's fine. You're sometimes correct about that. However, many people are incorrect about that. So to help us get to a point where we agree, what we ask from you to do is to submit code that's as close as possible to what you submitted and is also 100% correct. The idea would be that if you do that, then there is like a very clear sense of what you needed to do to get from what you actually wrote on the midterm to what you're asking credit for. Now, this is not a backdoor to get more marks for doing more studying after the fact. We would very much like for you to do that. However, we cannot, in fairness, let you do that. However, it is the way and the only way, according to this policy, in which you can make the case that you deserve more partial credit. Give us a solution that's as close as possible to what you had written, and that's also 100% correct. That will help you make the argument that the difference between what you wrote and what you should have written is very, very small, and you deserve more partial credit. So, again, kind of, if you deserve more marks, happy to give them to you. So it is a hurdle to submitting a request, to realize that. At the same time, I think it's good for you to do that as well, independently of whether you're getting more marks or not, because you're getting more practice. So that's kind of like the secret agenda behind that as well, in addition to the fact that we, without that policy, we got a lot of requests that are frankly not reasonable. So please follow the policy. So one more thing, I don't know if I mentioned it in 180. So on GradeScope, you see the rubric according to which you were graded. The way the rubric is set up is I make it up initially without really looking at a lot of solutions. I then send it to the TAs. The TAs then, as they grade, they discuss the rubric between themselves, they refine it, they add common mistakes, stuff like that. They say, okay, well, here's a mistake that I keep seeing, what do you guys think should be done in this kind of case? Stuff like that. And at the end of the day, we come up with the rubric that you see on GradeScope at the end. With that said, it's always going to be the case that sometimes the rubric doesn't fit neatly with what you have done on the midterm, right? So the most common thing that people, I think, in September ask me, what if I come up with a completely correct solution, but your model solution is completely different from that, but mine is correct as well? And the answer is, well, of course you should get 100% for that. And that's if that doesn't happen, that's just a mistake. But what can happen sometimes is that your solution is somehow so unexpected that it really doesn't fit with the partial credit scheme. So if it's 100% correct, of course it's 100% correct, there's no question. Sometimes you can argue, well, the solution that I had in mind is so different from what you had in mind that the rubric that you came up with for partial credit doesn't fairly apply to me. So that's an argument that I'm theoretically willing to consider. I emphasize theoretically willing because, again, you train people to write praxis essays for a semester and you let them make those kinds of arguments, you'll get all sorts. And not to say that some of those aren't reasonable, but not all of them are. So if you want to argue against the rubric, sure, I might or might not agree. So the last thing is, again, the usual. I think that, that's everyone. We reserve the right to regrade the entire midterm if you submit a regrade request. And the idea would be, well, the point is not to do a legal negotiation with you. The point is to give you the most accurate mark possible for the work that you actually did. That means that in principle, it should be that we were grading everyone's midterms again. Of course, then we'll grade them again and again and again. So we're not doing it. So in practice, the way I apply it is if the request is reasonable, and if I don't see anything by accident, I'm not going to regrade anything by accident. at the same time, on the extreme end, right? So someone requests a regrade for every single item because why not? Well, in that case, I'm not going to penalize the person for it, but at the same time, if you request, a regrade for the 10 items where you arguably maybe got a little bit unlucky, but on the other 5, you actually got lucky, but you don't request a regrade on that, well, the fair thing to do is to do all 15. If it's just the one, then, my intuition is that probably there's no point to looking at the other items as well. So again, like the upshot is you should never, like, if you think that there is a case to be made, you should submit a regrade request, of course. If your thinking is, I'll just try to argue everything, you can do that, but, well, we'll look at everything. Very rarely, almost never, does the mark go down. Sometimes what happens is if the person submits whatever, like 5 requests for 5 different items, I go through the midterm and I say, okay, like, yes, like you might have half an argument here and there you don't have an argument at all, but then there's half an argument for a question for which you didn't request the regrade that it actually should be lower. So net, it would be a change of 0. So that happens sometimes. I can't honestly remember when a grade went down. So yeah, that's the general thing. Questions, discussion, anything? Yes.
So we're supposed to send a correct version of the code.
Yes.
It's pretty much the same as what we roll out the video, or it's supposed to not.
So if your request, if you believe that according to the rubric you deserve more partial credit, not in general, right? So I'm not asking, like, so if you look at the rubric and you say, well, like, I believe that according to the rubric I should have gotten more partial credit, then yes, in order to request more partial credit according to the rubric, not in general or out of pity or anything, but according to the rubric, then we require that you send in the correct solution. Okay. And if it's too much of a burden, to be honest, well, you probably don't deserve the partial credit, because, like, if you deserve partial credit, that must mean that you've almost gotten the solution already. Yeah, all right. So that's that. Other questions? Yes. I have no idea. If you were the person who emailed me about it, I saw the email at 10. Have not had the chance to check, so I'll check after the lecture. All right. Okay, so we are continuing with dynamic programming, and we'll do the second. So we'll hopefully do 2 examples today. You'll continue one of the examples in the lab, and then the other one will be project 1. So project 1, we will not be ready to start project 1, like from the dynamic programming point of view, will be done today, hopefully. However, in terms of preparing you to do the C coding aspect of it, that would have to wait until next week, at which point we'll post project 1 so that, like, people don't get to start ahead of time just because they already know the material. So, all right. So next dynamic programming problem, and I guess it's like this problem becomes like less and less relevant with the years, but for this year we're still going to do it. And of course, again, it applies to other settings as well. So the problem is like that. So we have coin denominations, and it used to be that there was a penny. There isn't a penny anymore as of, I don't know, like 7 years ago, something like that. And then nobody uses any of the other coins anymore anyways, but in principle you have 5, 10, 25, you have the $1 and the $2, so just wrote it as cents. And what we want to do is we want to find a way to make a certain amount. So for example, 32 cents using the least amount of coins. Right, so 32 cents would be what? 25 plus 5 plus 2, right? So a bad way to do it would be 32 pennies. A not so great way to do it would be 3 times 10 plus 2. Right? So there's different ways, and one of them is the best. So specifically for for modern Canadian denominations, you can always do the greedy algorithm, what we discussed before. So sometimes it's the case that you could just say, well, 32, what's the largest coin that I can fit into 32? It's 25. So it's got to be that I can use a quarter. And then I have 7 left. So what's the largest amount I can fit into that? That's a nickel. And then I have the 2 pennies. So for those denominations, it does work. The reason this kind of algorithm that I just described works for those denominations is because you have singles, and everything else is a multiple of 5. So there is actually a theorem. It's not exactly trivial to prove that the greedy strategy of picking the largest possible coin every time works, but you can prove it. That's not true in general, right? So imagine a situation that's like this. So basically, imagine that the goal is 12 or something, and then you can have 4, or let's say you can have 7, and you can have 1, and you can have 5. Let's make it 11, right? So if you're greedy, you'll pick 7, and then you got to pick the 4 pennies. Because the 5 would not fit anymore. If you're smart, you'll do 5 plus 5 plus 2. One, yes. That was greedy and smart. All right. So for that kind of situation, it would not work. So some of you might know that in the 19th century, they had those kinds of situations. You had like various coins circulating. You had like the Spanish dollar was circulating, the doubloons, whatever that means, I don't know. There were all sorts of coins that were more like this. All right. So how do we solve this problem in general? So we have a list of denominations, and we are trying to make up a certain goal amount with the least amount of coins. So we can, again, set up a dynamic programming solution. So first, I'll just go over the notation. So we have the denominations. So this would be something like whatever, 1 and 5 and 10, whatever. And we have a target value. So now what we do is kind of similar to the houses problem. We're saying I'll set up a series of subproblems such that if I have solved those subproblems, I can also solve the big problem. Again, this is the creative step. It should not be obvious that you can do it like that just by looking at the problem. You need to think about it sometimes. So the subproblem and the common notation is opt for optimal. That's the least number of coins that you need in order to make up the amount B. Okay. So one obvious thing to say here is if you need to make 32 cents, opt of 32 is going to tell you how many coins you need for that. So if you know opt for any value, then you're good. You know how many coins. So the other thing is that the larger subproblems can be solved in terms of the smaller subproblems. So here's the idea. So let's go back to this. So we want to make 11, and we have 7 and 1 and 5. Right? So what is opt of 11? So the least number of coins. We can think backwards. I can say, okay, I need to make up 11, and it's definitely the case that I need to use some kind of coins for that, right? So to make 11, so yeah, there's not like a non-awkward verb here. I'll just use make, or like make up, I guess might be, I don't know. So we use at least one coin. So if we use 7 cents, then the number of coins is 1 plus opt 11 minus 7, right? Because the 7 cents, and then we also have 4 cents that we need to make up for still. If we use 1 cent, the number of coins is 1 plus opt 11 minus 1, right? Because you use the 1 penny, and then you still need to make up 10 cents more. How many coins do you need in order to make up 10 cents? Well, whatever opt of 10 is. And similarly, if you use the nickel, then you use 1 nickel, and then however many coins it takes to make 6 cents. All right. So, okay. So that suggests that we know the solution, right? Because what we need to say is, well, we are definitely using the 1 coin, and then, well, either this is the smallest, or this is the smallest, or this is the smallest. One of them is. So opt of 11 is going to be 1 plus minimum of opt 11 minus 7, 11 minus 1, 11 minus 5. Does that make sense? Because what we're saying is definitely use 1 coin, and it might be 7, it might be 1, it might be 5. And then if you use 7, then you need this many more coins. If you use 1, you need this many 1 coins. If you use 5, you need this many 1 coins. Right? So again, it might be obvious at this point or not, but it's not the case that you should always use 7. Right? 7 might be bad because it might be that opt 11 minus 7 is large. Because to make 4 cents, you need 4 coins, but to make 5 cents, you just need 1. To make 5 cents, yes, you just need 1. Right? So what corresponds to the actual solution is to use 5. So opt of 11 is going to be 1 plus opt of 6. And what's opt of 6, anyone? Yes, 2. Because 5 cents and 1 cent. All right. So that's the relationship between larger subproblems and smaller subproblems. Again, like the other day, you can think of those in terms of I'll just do a recursion, or you can think of those as I'll build up opt of 1, opt of 2, opt of 3, and so on. Those are equivalent. So let's just look at what the notation here says. So what's opt of V in general? Well, if V is smaller than 0, then it's impossible. So we'll just denote it with infinity. If V is 0, then it's 0, because to make up 0 cents, you don't need any coins. And otherwise, it's the minimum of 1. So you're using denomination di for the particular I, plus opt of b minus di. Is that making sense to everyone? Yeah.
In the slides, I meant to say 1 plus minimum rather than minimum 1 plus.
That's the same. Right? Because opt is always non-negative. So you can take the 1 out of the minimum. It's the same. Yeah.
And so I guess intentionally.
I mean, I said even if it were negative, by the way, it would still be the same. Yeah.
So I guess intentionally because this algorithm is for us to apply it maybe to adjacent problems. So beyond like maybe just like remembering this formula and remembering the general dynamic programming approach, what do you think is the best way to kind of think about
Yeah.
this?
So the question is, and you're right. So I would say, so I think the term you used adjacent. So I would say the general philosophy is you come up with this kind of formulation for opt, and that might be different for different problems. And then you come up with a recurrence. So what I'm doing here is like, I'm just giving you several examples. There's going to be several more coming up. And hopefully that gives you a feel for what to do. In general, it could be a quite difficult problem to solve, right? So there's not a general algorithm for like, here's the word problem and here's how I map it to the formula. That just doesn't exist. If it did exist, there wouldn't be not a lot of point to teaching it because it would have been implemented already in Python, whatever, right? So the general approach is you try to say, okay, like what is a function like opt where if I plug in the appropriate v, it will just give me the solution to the problem I'm looking for, and in such a way that I can relate opt for larger problems to opt for smaller problems, right? So another way of thinking about it is just without the algebra, just saying, okay, like I need to paint the houses or I need to make up kind of a sum using the coins. If I knew how to solve the small problem, I hope that I would be able to solve the larger problem. So you're saying, okay, like if I divide up the problem somehow, am I going to be able to do anything with it, right? So I guess one kind of intuition I can give you is this is not the only way to divide the problem, right? So another way to say it is, well, and that's the worst way, but maybe it's still worth looking at. Is you could say, okay, so 11, what is 11? Well, it's like 0 plus 11, and it's also 1 plus 10. And it's also 2 plus 9 and so on, right? And one of those ways is the way to break up 11, right? So I can say that therefore opt of 11 is the minimum of opt of 0, which is 0, plus opt of 11, which is not super useful because that's an infinite recursion. And then also opt 1 plus opt 10, and so on, right? So what I can say is I'm going to try to break up the problem of making up 11 cents into, well, like I'll just break it in half and I'll make up one half, I'll make up the other half. Well, half is maybe a bad term because they're not halves, right? So that is also mathematically true. It's not as efficient because what I did here is I just said, okay, well, like I'm not just breaking it up randomly into two different parts. I'm saying one of the parts has got to be one coin. But this would also work. Does that make sense? So, all right. So anyway, Okay, so that is the formula. Is everyone comfortable with the notation here? Is there questions about like the formula? Yeah.
Why do we use infinity for v less than 0?
Yeah, why do we use infinity for v smaller than 0? And the answer is, suppose that you're trying to make up. So suppose that the goal is 4, or well, whatever. I typed 3, but suppose the goal is 4. Then I could, in principle, just naively say, well, it's 1 plus opt 4 minus 7. Right? So what's the best way to make 4? Well, I'll use the 7-cent coin, and then I'll make up the -3 later. Right? So if I don't define opt of -3 as extremely expensive because it's impossible, well, it's got to be something. Say again?
It's just gotta always be, when you put in the minimum function, it's always two discrete.
Yeah, exactly. Yeah. So so the idea is that 1 plus opt -3 should be a bad option. Does that make sense? So, all right. So that's like that. So in the lab, I asked you to actually implement this. So I think I want to get you started because some of you are going to be doing it in like 15 minutes. Let me say. And I'll call it using make change. For example, sure, 1 to 5. Well, so that's like the easy one. So like I'll say like 175 and 11. I wonder if Copilot, yeah, Copilot knows that. That's amazing. Okay. So that's our goal. Is that large enough? Is that okay? Okay, no complaints. So, okay. So what do I want to do here? So I want to set up the opt array. And that's going to be like this. So y plus 1, anyone? Yeah. Yeah, because I want opt of 11. So I want to go from 0 and up to 11. Okay. So 0 here is actually unideal because some amounts you can't actually make up at all. So what I'll do is I'll set it to infinity. So to get infinity, I'll just say. All right. So this is now 12 infinities, right? I assume this is 12. Skewering a part of it. All right. So now, so the formula, I'll just remind you from the slides. So opt v is the minimum of 1 plus or C in coins, right? So that's the form. Make sense? Also opt of 0 is 0 because to make 0, you just need 0. Make sense? So what I want to do is I want to get the smallest possible value for this guy. Right? So, all right. So this, in fact, actually works, but I don't want, well, like if you want to do it like that, that's fine. But basically, okay, so like let's do it like that. I will type it in like that. This is a list comprehension that actually works. But please but please just like expand it into a for loop so that you actually understand what's going on. Okay. So this is saying what you think it's saying, which is get me the minimum of this formula. In practice, what it does is it just computes all the values. It leaves out values where j minus c is not greater or equal than 0. And then out of all the values for every possible c in coins, it takes the minimum. Right? So the plan would be, once you have opt of 0, you can do opt of 1 using this formula, then you can do opt of 2, opt of 3, and so on, up to opt of amount. And opt of amount is the answer to what is the smallest amount of coins that you need in order to make up AMT. So that's not the same as actually having the answer, right? This is just saying this is how many coins you need in the answer. So how do you get the answer? Same strategy as with the houses, you work backwards. Right? So suppose that you know that the number of coins needed for V is opt of V. So to make 11, what coin should we definitely use if we know opt? Well, you can just say, which is the smallest? Is it opt of 11 minus 7, or is it opt of 11 minus 5? Or is it opt of 11 minus 1? Whichever one is the smallest will tell you which one of the coins should you definitely use, right? So in this case, what the smallest is opt 11 minus 5, because that's just 2. So that means that in order to make 11, you definitely need to use 5. It's this one, right? And then the next question is to make 6 cents, which is what's left after you've used the 5 cents. What coin should we definitely use? And you can do opt 6 minus 7, which is negative infinity. And there is opt 6 minus 5, which is 1. And there is opt 6 minus 1, which is also 1. Right? So this is the same as this, which makes sense because you can use either a 5 or a 1 there. You'll just use the other coin next. So you can use a 5-cent coin and you can use a 1-cent coin. And let's say you picked 5. So the next question is to make 1 cent. What should you definitely use? And you can try opt 1 minus 7, opt 1 minus 5, opt 1 minus 1. And you should definitely use right. So you repeat this process until you've made up the sum that you wanted to make. So that's a while loop. Yes.
In the first step, do we also use 11 minus 1?
Yeah, you're actually right. Yes. And that would be because this is 2 and this is also 2. Yes. Thank you. All right. So this is a for loop to compute opt of j. And then you do, once you have the opt, you can do a while loop to compute the optimal solution. There is a way to do both of those things simultaneously. It's just annoying. So I'm not making you do it yet. All right. So basically the way you would do it is you would like every time you compute opt of j, you note down how you actually did that. Right? Because like that information is there. Like you just need, so here when I'm saying minimum, I'm discarding the information about what coin I used, but I can just note it down. It's annoying to do, but you can do it. Make sense? All right. So that's the coins. Questions about this? All right. So I'm going to introduce the thing that we're actually going to be doing in project 2. And we're going to do it in kind of several goes, I guess. So first, I'll just introduce the mathematical model. So the mathematical model is like this. So we have this graph. So basically we have, a bunch of nodes and those nodes are connected. And then each of the edges, so each of the arrows correspond to a cost. So it costs me something to go from here to here, and it costs me something to go from here to here, and so on. And what I want to do is I want to find so what we call a seam that will make sense next time, that costs the least amount possible, right? So again, like so kind of to go from here to here costs something, and to go from here to here costs something, and I want to get from the top to the bottom somehow. So like think about it as, Google Maps is trying, so it's not exactly that, but like Google Maps is trying to find a way for you to get from the top to the bottom. Yes. All right. To the code or? Yeah. Yes, because j is so like 0 and then 1, then 2, then 3, and so on. Wait, like that's because it's like I'm not doing your homework. This is your lab. Yeah. You're welcome. So okay. Yeah, so it's not. You're right. It's not complete code. The reason it's not complete code is because it's your job to complete it. So okay. So this is what we're trying to do. So it's different. So I'll give you the setting next time, but it's different from kind of the Google Maps task in that you want to get some kind of path from the top to the bottom. You don't care where you start at the top. You don't care where you end up at the bottom. You just want a contiguous path. So how can we do it? So I think, so there's 4 minutes left. So like really not enough time to talk about it. So I'll just give you a preview. The terms here are a little bit weird, but that's like Shai Avidan and friends who invented it. That's the names that they gave. So okay. So the cost of going from here to here is called the energy, and we want the minimal energy path. And what we want is the minimal energy path from J, from J to from Ji to the bottom, right? So here you are like at J equals starting from one. Well, this is like not symmetric. So here it's like J is 2 and I is 4, for example, right? So Ji is the coordinates starting from the top left. What we're defining is what does it cost me to from over here to the bottom somewhere, right? And the claim is, well, in order to get to the bottom from here, what I need to do is I need to first get to here. And then I need to either go here or go here or go here and get to the bottom. Make sense? So that means that the total cost of getting from here down to the bottom is whatever it costs to get to here, plus the minimum of getting from here to the bottom, getting from here to the bottom, getting from here to the bottom. And that's the formula. All right, so we'll do this next time in more detail, and then you'll implement all of that in C. Doesn't that sound fun? All right, I will see you on Thursday. Bye.